Okay. Can you hear me well? So great. Oh, so it should be 16 to 9. Well, it's fine. It's 3 to 4. I think it's okay. Good afternoon, everyone. My name is Bozhen Liu from Texas A&M Corpus Christi. We are another campus of the A&M system. And here I'm presenting this paper, right, GoGuard. Well, I think most of us, we are not strange to concurrency bugs, right? And Go, as a relatively new programming language, it introduced a lot of synchronization primitives, right? Makes developers' life easier and hard because it introduced new types of Go-specific bugs based on the fact that we already have a lot of traditional concurrency bugs we need to detect, we need to deal with, right? For example, I list some here. These are not the full list, just some classic examples. And later, Tool proposed a new classification for concurrency bugs in Go programs, right? They divided them into blocking bugs and non-blocking bugs, right? The blocking here means one or more goroutine, the execution is stuck and it cannot proceed anymore, right? So based on this classification, most of the recent research effort is put on this Go-specific blocking bugs. Most of the time, it's channel-caused blocking bugs, right? And meantime, existing classic works, they still works for detecting traditional concurrency bugs for Go programs. For example, this ABBA lock, double lock, right? The problem is because of this classification, the existing two groups of works, they separate. They have different emphasis on bug detection, so they can miss true bugs. Another reason is because the real-world scenario, concurrency scenario, is complex in real-world programs, right? You can have channels, you can have logs everywhere. They somehow conspire to conceal each other, right? They are mixed together. It's not only channels or only deadlocks there, right? So the key demand here is we need something that can unite the communication behaviors of traditional concurrency bugs and Go-specific blocking bugs, right? So we can detect them together, both of the type of bugs together. And that is the motivation of GoGuard, right? It unites the presentation, the communication of Go's synchronization primitives. Well, here, these primitives include logs, mutex, channels, conditional variables, blah, 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 a lot of them. Well, GoGuard for now is implemented to detect blocking bugs, but it has the potential to detect non-blocking bugs as well. And we compared with the state-of-the-art tool GCatch, and we have the similar performance based on the evaluation on the whole packages, and we can detect the 10 more true blocking bugs. These blocking bugs are coming from real-world large Go projects. So our tool is publicly available on GitHub here. So next, let's take a look why it works well on detecting blocking bugs, right? Including traditional blocking bugs and Go-specific blocking bugs, right? I think we are all familiar with this problem, right? Producer, consumer, right? Anybody don't know about it? Right. So the key thing here is we want to let producer produce pizzas all the time, put them in a shared buffer here, right? And producer and then consumer can take pizza out, right? So this flow can continue when we have pizza, which is this task or messages from producer, as well as we need to have consumer here, customers here, right? So anything missing will block this flow here, right? So this blocking, this concept here is really, it aligns really well with Go's synchronization behavior. This is like a intuitive example of Go's communications, right? So for example, here on the left-hand side, we have this producer. We have a chef mouth, right? So we send pizza into this channel. And through this channel, we have two producer, right-hand side to eating the pizza, receive the messages, right? So here, the channel send operation works as a producer, and these two consumers are receiving messages here, right? So that is one example. And this concept also goes well with the classic mutex, right? So when we have an unlock, we can see it as a producer which released a lock object, and then this object can later be obtained by a lock from another thread, right? So the unlock here can be a producer and the lock can be a consumer. So somehow we can map the Go's synchronization primitives, their statement, their creation, into this resource producer-consumer relationship. Right here, we enclose this channel, mutex, context introduced by Go, wait group package, which works like this thread start and join. No start, just join. And sync new condition is the conditional variable in Go, right? So here includes most of the major Go synchronization primitives. And the resource here, we identify them as this object, like for example, the object of channel, the object of the locked variable, right? And we also identify the producer statement, for example, the channel send, and the consumer, like the channel receive, right? So this is somehow the foundation for the later we can detect the blocking bugs using this theory. And one thing good here is that this concept unites the traditional and Go-specific concurrency primitives and formulate their control flow into a single general form. Right, so we can leverage this to detect channel-caused blocking bug and mutex-caused blocking bug. And as we all know, statically, if we want to detect some bug, we need to know the happen before relationship among a multi-goroutine thread program, right? So we developed this resource flow graph, including two types of messages here. One is this producer-consumer relation we introduced in previous slides, as well as the static happens before relation, which is necessary to detecting bugs, right? So let's see a small example here. The code is a little, I tried. The code is a little tiny. Let me explain a little bit. So we have three goroutines. Main goroutine spawned two goroutine, and all the three goroutines communicate through channel and sync wait group. So here, right-hand side, we have this example RFG graph here, right? It includes the happen before relations, right? For example, the main goroutine spawns the Go1 and the Go2, two goroutines, and when they end, which indicated by the exit node. And meanwhile, we also include these channel send and receive operations from this program. Right, we create a node to represent them, as well as these weighted group nodes. Right, one thing to note that is defer wg.done works as thread join is always executed at the end of the goroutine. So instead of creating new node, we just use the exit of the goroutine to represent it. And continue. So how can we leverage such a graph to detect blocking bugs, right? The key insight here is a consumer always blocks the execution of a goroutine unless a producer from the same resource can match with it, right? This is a really simple idea, and this somehow guides our tool. And during this detection process, we are maintaining a set which is called heap. It keeps track of the Go routines that can happen in parallel. And one thing different from existing approaches is that instead of enumerate all possible Go routines or possible producer-consumer pairs, we only choose a goroutine randomly from the heap when there are more than one goroutines that can happen in parallel. Yeah?
When you say randomly, is there some fairness hypothesis?
Race?
On the random choice, is there some fairness hypothesis? Is it fair choice or
No, it's
unfair? You can choose always the same.
no, we will not always choose there. Yeah, it's a fair, right? Right. Thank you for the question. And continue with the simple example. Let me explain how this ship works, right? So how we detect the blocking bugs. So we will traverse the graph starting from the beginning, the root node of the graph, which is main node, right? So before we traversal, the heap is an empty site. There's no goroutine there. After we visit the main node, the heap will be updated to main, and continuously the next two nodes would be the go spawn statement, right? Go 1 and go 2, and then we update the heap to main go 1 and go 2. And for now, that's it. And then we continue the traversal along this age, right? Because we are going to stay in one goroutine for now. And next we see this WG dot, my mouse is gone, WG wait node, right? This wait node in our concept, it's a consumer. Consumer needs to be matched with a producer, but for now we haven't seen any producer to match with this WG wait node. So we cannot proceed. So we'll pause our traversal for main goroutine here, and we'll come back later. And next, we're going to pick a goroutine from the heap to traverse again, right? So let's say we'll pick go 1 to do next, right? So we'll traverse go 1. And here we see this CH send at line 3, right? A channel send operation. It's a producer in our concept, right? So for a producer, we need to match with its consumer. So resource-wise, we have two consumers here, right? I use the orange node to highlight them, right? One is in Go routine 2, the other is in the main Go routine. So for now, only the one in Go routine 2, that is a correct match with this producer. So because only those Go 1 and Go 2, they can happen in parallel, indicated by the heap, right? And then we find a match, and then we can continue the traversal and reach the exit of the Go routine 1. And we remove Go 1 from the heap, right? We finish its visit. And continuously, we will pick the only one remaining Go routine from the heap set, which is Go 2. And we continue traversal. We see this CH receive at 7, right? It's a consumer in our concept, right? Since previously we already find its producer, it's matched, so there's no need to pause the traversal. Nothing will stop it, and we continue and timer. My? Okay, so it's my alarm. Sorry, I have another meeting scheduled. Sorry. So, and we continue and reach the end of the Go routine 2, exit, and we remove Go 2 from heap. Now we'll come back to the main Go routine. We haven't finished its traversal, right? So we were stopped at this WG wait node, right? And it needs its producer. Who are their producer? Exit 1 and exit 2, right? Because they represent this deferred WG.done, right? It's a thread join. It works like a thread join. So producer and consumers, they are matched. And then we can continue the traversal in main Go routine. And here comes the problem. We see another consumer here, right? This consumer somehow, we have no more producer. We have no more channel send operations on the same resource. We cannot proceed anymore. So somehow this indicates there's something wrong with the program, and it blocks here. So we'll report this to the developers. This is the blocking bug. You need to handle it, right? That is a simple example to explain the process. So for sheep, there are advantages, right? We introduced this randomness, which is somehow very similar to the real world scenario, right? In real world distributed parallel programs, we have many random schedules, right? However, we also have disadvantages. The major one is they also add this random selection of goroutines when we picked for traversal every time, right? So these randomness can cause false positives and false negatives because we didn't enumerate all possibilities here. However, we would like to argue that we can implement SHIP to explore all possible concurrent goroutines and all possible matched producers and consumers here, which will make our tool sound. At least there will be no false negatives. False positives we cannot avoid for static analysis. That is our tool for detection. And instead of that, we also have many optimization and heuristics added. So all these optimizations and heuristics, we observe them from real-world projects, right? So all these are here to fasten the process of detecting blocking bugs. We implement our techniques based on Go 1.17 and the Go tool, while we adopt the origin-sensitive pointer analysis for identifying the resource, right, matching the resources, right? So this is a pointer analysis that's goroutine sensitive. So it works better to identify channels, logs created in different goroutines. And we also compared our evaluation with GCatch, the state of the art. We have two sets of benchmarks. One is GoBench. It includes 66 blocking bugs extracted from real-world large Go projects. And also we evaluated some recent commit from real-world large Go projects. For example, gRPC, etcd, Istio, and surfing. So here we report the evaluation on GoBench, right? So on the left-hand side, this table lists the benchmark set from GoBench, and highlighted two columns are the number of blocking bugs we detect by using GoGuard, our tool, and GCatch, right? The bug is reported in the form of true positives and total numbers of detected blocking bugs, right? So as you can see, our tool can detect 61 out of 66 bugs from the benchmark set. However, GCatch only can detect 10 out of them. While the time performance is also difference, right? GoGuard only use 35 milliseconds for this benchmark set, while GCatch needs a little longer. And we further distinguished what types of blocking bugs GoGuard and GCatch can detect, right? Which is listed on the right-hand side table, right? There are basically three types of blocking bugs: communicate-based, mixed, based, and resource-based deadlocks blocking bugs, right? So as we can see, GoGuard can work well. We can detect almost three types of those blocking bugs, right? Well, GCatch is designed to focus on communication and some mixed types of blocking bugs, but it's not that ideal. And we also evaluate our tool on real-world Go projects. And on the left-hand side, we report the numbers of detected blocking bugs for real-world programs. Right? GoGuard reports 12 true blocking bugs with 16 false positives, while GCatch found two true positives out of 14 reporting blocking bugs. So this is something we didn't expect also when we evaluated the program. And this also indicates the fact that we need some algorithm that can unite the detection of different types of blocking bugs. The classification somehow prevent us from finding true problems in the real world programs. And on the right-hand side, we listed the statistics of this RFG graph we have when we evaluate the Go programs, right? As we can see, so many channels and logs interactive together in the program. Somehow, it's necessary to consider them together. Here we report the performance of running GoGuard and the GCatch on real-world programs. So we report this in the form of average time versus maximum time. And here we compare the performance on the whole packages, right? Since GCatch will scan every packages in a project, we'll do the same. And well, we have some good and bad, but in general, our performance are on the same magnitude on average. So this presentation, I introduced this GoGuard tool, which includes these 3 things we developed, right? RFG graph, shapes, and some optimizations and heuristics. And this GoGuard is designed to detect the blocking bugs, for example, channel cost, ABBA deadlock, double log, mixed style of logs. And that are something we already explored. Next, we would like to do is to extend this concept on detecting non-blocking bugs. For example, data races, race conditions, those classic concurrency bugs, right? So that is all my presentation. Thank you, and welcome any questions. Yeah, we have these optimizations, right? Right.
How do you understand? How can I guess what you do from this sentence? Loops on the
Yeah, so that's
it's a sequence of assertion explaining nothing.
Yeah, well, I try to keep everything simple. So.
Okay.
Oh.
Can you explain?
Yeah, sure. So how we achieve this loop sensitive for goroutine is we have 2 parts, right? One part is pointer analysis. We identify the goroutines spawned inside the loop, so we will create 2 goroutines, 2 contexts for each goroutines. So then the channel objects, the logs, all the objects and variables created inside that goroutine will have its own label. Right, so that at that time, goroutines found inside a for loop, we can distinguish them. So that is one part how we handle for loop. And when we do the detection, it's the same. So we'll also, well, assume we have these 2 goroutines are spawned inside a for loop. We'll also, based on the information provided by pointer analysis, we will be able to distinguish there are 2 for loops, and we'll create 2 of these goroutine graphs inside our RFG.
If we work only the loops are synchronous in 2 processors, whereas the problem is in one iteration you may communicate with some input of the other process, or the next you communicate with another one, and so there might be no regularity, and then what you do seems not to work in that case.
Could you please?
The example you showed explained was the loop are synchronous. At each iteration, some point in the loop correspond to some input or output of the iteration in the other process. But usually in one iteration you read something, next iteration you read some other thing, and so the things are not regular and depends on the tests that are done inside the loop. And so I don't know how you can handle this.
Yeah, that is true. Well, because here we have some handlings of that information, right? So most of the time when each iteration. For the case you mentioned, it's like in a switch case.
We have a select some kind.
Yeah, we'll have a switch case. Right.
The other you don't know.
Yeah.
Except if your analysis is
Yeah.
very precise.
So for those cases, we'll enumerate this matching. We will have different state. We will store those state, pairing with different producers and consumers, and explore them later.
Okay, so you will end up everybody can correspond with everybody else.
Yeah, right.
Which is not enough. For example, if you have one process that waits for another one, that waits for another one, that waits for another one, that waits for the process first one, we will not have it.
That is a really complex case, yes. Yeah.
Thank you for your talk. If I got it correctly, there are still a few blocking bugs that are not detected. And if I got it correctly, they are all inside Kubernetes, the Kubernetes example. Could you please go to that slide?
Which one?
Yeah, a bit further. No, in the other direction, I guess.
Huh? Go forward, backward?
Yeah, forward, please.
Here? No.
Yes. So here in the Kubernetes line, it seems that all of the blocking bugs that are missing are coming from the Kubernetes example. So yes.
This one?
Yes.
Uh-huh.
And I don't know, is there some sort of specific pattern or?
Yeah, that's because we have those random selected goroutines, and sometimes we couldn't select the correct goroutine, so it will miss the bug. That is how we have some missing here, right? We missed 5 of it here, right? But if we update the tool to enumerate all possible goroutines, and instead of randomly selected, we can do that. But that would be very expensive because it would be large space to explore, right? We don't want to sacrifice that performance, so we picked this to implement, right?
Okay. Last question.
You showed the runtime for your tool, and you are doing the pointer analysis also. So is the runtime of pointer analysis included in that?
Right type of pointer analysis is another work published.
No, you are using origin sensitive pointer analysis, right?
Yeah, right.
So when you show the runtime of your tool like GoGuard, does it also include the runtime of computing the points to analysis, or it just uses the results as a client?
Yeah, it includes the time of running pointer analysis, and actually running pointer analysis takes a longer time, takes a large portion of the whole detection time, right?
Okay, yeah. Thank you.
You're welcome.
Okay, let's thank the speaker again.
Thank you.